At this point, we are next going to talk about integer programs. I've got some suggested reading up there if you'd like from Robert van der Bij's book. An integer program is just a regular old linear program, but with an additional restriction that all of the variables have to be integers. Okay, so it looks just like a linear program. You've got the same objective function, linear constraints, and so forth. And this happens to be in standard form, but it doesn't have to be. But you have this extra condition that all of the variables have to be integers. This is a natural constraint that has come up already in certain problems a handful of times, right? If the baker can't make a half of a cake, for example. If you're a factory making, battleships or submarines, a half a submarine doesn't mean a whole lot. You're also going to encounter mixed integer programs. A mixed integer program is an integer program where some of the variables are allowed to be continuous. So mixed just means you have some variables that are integer, some of them are continuous. Unfortunately, unlike a linear program, which we've now seen is pretty easy to solve, or pretty straightforward to solve algorithmically, integer programs are a lot harder. The technical term for that computer scientists use is we say that integer programs are NP hard, which just means it's as hard as a certain well-defined, very broad class of problems. In fact, even if you get rid of the objective function, even if you just say find any integer solution to a system of linear inequalities, that is still NP hard. And I have two diagrams here that illustrate various principles. It's natural to think, well, wait, can't you just solve the linear program and round it or something like that? And none of those techniques actually works. So what I've got here in this first diagram here on the left is I've got a feasible region here that you might encounter when you're performing the graphical method. And then I've highlighted all of the integer points within that region. And so whereas the linear program has this convex, nice, well-shaped, in this case, pentagonal region as its feasible set, the integer program just has this discrete set of 7 points. This example on the right, I think, is even more extreme. This is an example where you have a linear system. If you look at the linear relaxation, you'd have this sort of skinny, sharp, pointy, triangular shape. But there actually aren't any integer points that lie inside this feasible region on the right. So this problem on the right would be an example where you have a system of linear inequalities that is feasible, but becomes infeasible when you require an integer program. And so when that happens, you're pretty unhappy because you run out of feasibility. So, all right, let's try the natural kinds of approaches here and see where they break down. Rounding, right? The natural thing that anyone is going to do when you describe this problem to them is they'll say, well, let's just take the linear program version of the problem. Okay, forget about the integer constraints, solve the linear program, and then just round it, right? Just round the entries of that to the nearest integer and see where that gets you. So number one, that might not even be feasible. Okay, problem number one. Problem number two, even if it is, there isn't a guarantee that you're at an optimal solution. So I've got an example of a two-dimensional linear program here that we'll look at using the graphical method. And if I were to solve this linear program, or if I were to solve this problem disregarding the integrality constraint, you'd find your solution right here. And if you were to round that solution, you'd arrive at this red point over here. But the optimal solution to this integer program is actually all the way down there at this green point. So this is an example where rounding does not get you very far. And this problem becomes way worse in higher dimensions. Okay, it looks like you could circumvent it in 2 dimensions, which you could, but it becomes much, much more difficult as you raise the dimension. Here's a second example of another integer program where when we look at the solution here, you'll find that the linear programming solution there, the solution to the LP lies on the corner here. You round it, you get a point that is not feasible, and the optimal solution is this green point over here. So I've used this term, I'll say it again. When you have an integer program and you disregard the integer constraints, we call that the linear programming relaxation because you're relaxing the integer constraints. So what I've just described is, or what I've just been comparing so far, is the difference between a linear programming relaxation and an integer program, or an integer program and its linear programming relaxation. The most common instance of an integer program is a binary integer program. That is one where all of your variables have to be either 0 or 1. Okay, that sounds like an easy problem, but in high enough dimensions, this gets to be a real challenge. Now, it's natural to say, well, why is this an interesting problem? Right? I care about whether I'm buying, 500 gallons of oil, not whether I'm buying 0 or 1 of these things. And the reason these are so useful is that you can use binary variables to model logical constraints, like yes or no decisions. Anytime where you have a yes or no decision that you have to make, there's some way of modeling the various conditions that arise using these binary variables. And we'll go through lots of examples here. So I should say that these variables are also called indicator variables because they indicate whether you're doing something or not. So 0 is no, don't do the thing, or 1 means yes, do the thing. So let's do some examples of this. And it's a good idea to pause at each one of these and try and work out the answer for yourself, but we'll just go through them. So let's say x1 through xn are indicator variables. So x1 is equal to 1 if you do a thing, and then 0 otherwise. So how would you do a constraint that at most one of x1, x2, and x3 is allowed to occur? Right? X1 is the variable that I take my dog for a walk. X2 is the variable that I read the newspaper. X3 is the variable that indicates if I polish my shoes. And I only have time for one of those things, let's say. So how do I model a constraint that at most one of these things occurs? Well, not surprisingly, you just say they have to sum to less than or equal to 1. Right, less than or equal to, because the way that statement is written, you're allowed to do none of those things, right? You're allowed to do 0 of them. That's fine. The constraint, as it's written verbally, just says that at most one of those things can happen. Okay, number 2, the second bullet is kind of a funny one because it's actually very simple, but it's worded in a way that makes it sound more complicated. Either x1 and x2 both happen, or neither one happens. Okay. Good idea to pause this one and think about it for a minute. Either they both happen or neither one happens. This is actually just a fancy way of saying that x1 is equal to x2, right? This is a classic example where your customer tells you something and they phrase it in a way that makes it a little more opaque than when you actually look at how it's written mathematically. Then you're just saying x1 is equal to x2, right? Because x1, whatever happens with x2 also has to happen with whatever happens with x1 has to happen with x2, and vice versa. Let's do implication. That's the third one. If x1 occurs, then x2 must occur also. So it's tempting to say, well, why isn't that the same as this one up here, right? That x1 is equal to x2. Well, there is a distinction here in this third one. I've said if x1 occurs, then x2 has to occur. But if x1 does not occur, then I don't have any information about x2. So if x1 is 1, then x2 is 1. But if x1 is 0, then x2 could either be 0 or 1. So there's no condition imposed when x1 is equal to 0. And once you see the answer, I think it's pretty intuitive. The answer is that you say x1 is less than or equal to x2. Okay, this gets exactly what you want. When x1 is equal to 1, that forces x2 to be 1. But when x2 is equal to 0, this constraint doesn't tell you anything. Okay, this last example here is basically the same as the first example. At least 2 of x1, x2, and x3 must occur. These x's have to sum to something greater than or equal to 2. Now, it's natural at this moment to look at these examples and say, okay, is there kind of a broader system here? Or what, is there a general rule set for how I can take any kind of logical sentence and write a system of equations or inequalities? There is, and that's what's covered on these slides here. And we do have an optional lecture that you're welcome to read if you'd like to go through this. In the interest of time, because we are forced to compress 15 weeks of instruction into 13, I'm not going to bother getting into this with you because I think we can have just as rewarding of an educational experience without it. I will post some optional material on that, but let me skip forward here. I want to rather just do lots of examples and try and communicate that to you this way. So we'll go through this here, and I just want to show a few examples. Here, I like this one. Here's another few examples that we'll look at. If x1 is true, then y1 through y4 have to equal 3, and if x1 is false, then y1 summed through y4 has to be equal to 4. Okay, you can imagine that, right? If x1 is true, then you're buying, one factory, and then you have to make this many units. And if you don't buy the factory, you have to make a different number of units, right? You can imagine situations where this would happen. The way you would model that constraint is this thing here. You'd say the y1s summed together, they are equal to 3 times x1 plus 4 times 1 minus x1, right? What does this accomplish? If x1 is false, then this thing gets zeroed out, and you have the y's have to sum to 4. Sorry, if x1 if they sum if x1 is false, then these things sum to 4, as I've written there. Sorry, my eyes lost track of the slide. And if x1 is true, then these y's would sum to 3. And now I'm going to erase all these markings here to try to make this clear. All right, so that's how you would model a kind of conditional equality constraint, right, where an equal sign that depends on the value of a variable. The same thing also works just fine with inequalities. You could take the exact same statement but replace the equal sign with a greater than sign, and you get just what you see here. Nothing surprising there. This next example is a little more sneaky. x1 is true if and only if the y's sum to something that's at least 3. Okay, so what works out here? Another way of writing that would be as follows. x1 is true if and only if y1, the sum of these y's, is greater than or equal to 3. Okay, so what could we say about this here? We'll say that if, on the one hand, if x1 is true, then the y's have to sum to at least 3. There's nothing new there. And then also if x1 is false, then what's true? Then the y's have to sum to less than or equal to 2. We're going to assume that these y's are all integer variables. Okay, so if you're not greater than or equal to 3, then you're strictly less than 3, which if the y's are all integers means they're strictly less than or equal to 2. So then the y1 plus y2 plus y3 plus y4 is less than or equal to 2. Okay, so how do we accomplish this here? We'll do each one of these expressions separately. So the first expression, okay, the one that says if x1 is true, that is, we've already kind of dealt with that in the examples above. That just looks like this, right? That the sum of the y's has to be greater than or equal to 3 times x1, right? Because if x1 is true, then this says the y's are at least 3. If the x1 is false, then this says nothing. It says the y's are greater than or equal to 0, which is always true. Okay, but now let's look at this next one. If x1 is false, then they have to sum to something less than or equal to 2. And I claim that this bottom expression is what captures that. Okay, what have I done here? I've taken a 2, which is the 2 on the right-hand side of the constraint we want. We want to be less than or equal to 2. I took that 2, and I multiplied it by 1 minus x1. Right? What does this do? If x1 is false, then 1 minus x1 is 1, because x1 is 0. And so this thing becomes a 2. And if x1 is false, again, this thing gets zeroed out. Okay, so if x1 is false, then the right-hand side here is a 2. On the other hand, if x1 is true, then what happens? Then this thing here on the right gets zeroed out, and this just becomes a 4. But look, there's only 4 variables here, right? So there's 4 variables, so the most they could sum to is 4. And so by saying y1 sum to y4 is less than or equal to 4, I'm not actually, there's no content to that constraint, right? I'm not saying anything useful there. So these constraints put together are a way of imposing that kind of condition. Or x1 is true if and only if the y is summed to something less than or equal to 2. You could look at this example as well. It's exactly the same the same kind of logic there. Nothing terribly exciting. We have plenty more examples of this. If x1 is true, then the y's have to sum to 2. If x1 is true, then y1, y2, y3 has to be equal to 2. And we'll say if x1 is false, then there is no constraint. Okay, let's think about that. The answer to this one is that you're going to take this statement that the y's have to sum to something equal to 2. And a good way to attack this is to break this equal sign into two inequalities. If I say that they have to be equal to 2, we'll say that's the same as me saying they're both less than or equal to 2 and greater than or equal to 2. And then we'll look at the rules from the previous slide and work that out. And it turns out the way you would model this is you'd say 2x1 is less than or equal to y1 plus y2 plus y3, and then 2x1 plus 3 times 1 minus x1 is greater than or equal to y1 plus y2 plus y3. Let's look at this a little more carefully here. First of all, let's try the case when x1 is true. Okay, what happens when x1 is true? When x1 is true, then you get a 2 over here. Okay, I'll cross out that x because we don't need it. You have a 2 on this side, and then this whole expression here gets zeroed out because x1 is equal to 1, and then you get a 2 there. So you have 2 is less than or equal to the sum of these y's, and then you also have 2 is greater than or equal to the sum of these y's, which is just what we wanted it to be. On the other hand, what happens when x1 is false? Let's work this one out. I'll erase some things here. When x1 is false, you have a 0 over here. Okay, so this first constraint has no value to it, has no content. It just says the y's are greater than or equal to 0. And the second constraint, this thing also gets zeroed out, and this says the y's have to sum to something less than or equal to 3. And again, since there are only 3 of these y's, you know that the answer is, or that the constraint has no teeth to it. So as I said, there is a system in place for like studying these kinds of expressions in a sort of rigorous, exhaustive way, which we're not going to cover this semester. But what we're going to do instead is just try to get enough practice with these sorts of expressions that we're comfortable manipulating them in the ways that I've done. This is a puzzle called The Knights and the Werewolves by Raymond Smullyan. Actually, he wrote books and books of these kinds of puzzles. It's just every possible configuration of this brain teaser about, you're on an island and some people always tell the truth, some people always lie, this kind of thing. So this is one, and we're going to talk about how you could solve this kind of logic puzzle using integer programming. In fact, it's actually very versatile for solving lots of different puzzle-type games, as we'll see later on in the lecture. This puzzle works like this. You're visiting a forest in which every inhabitant is either a knight or a knave. Knights always tell the truth and knaves always lie. In addition, some of the inhabitants are werewolves and have the annoying habit of sometimes turning into wolves at night and devouring people. A werewolf can be either a knight or a knave. So you're interviewing 3 inhabitants, 1, 2, and 3, and you know there is exactly 1 werewolf, and that werewolf is also a knight. And they tell you the following. So number 1 says at least 1 of the 3 of us is a knave. And number 2 says 3 is the knight. And based on those 2 statements, we need to figure out who the werewolf is. All right, so it's a logic puzzle, and we're going to use CVX to solve it. We want to figure out who the werewolf is. So what the way we'll do with this, or one way we could do it, is to let x1, x2, and x3 be the variables that indicate if each person is a knight, and we'll let y1, y2, y3 be the variables that indicate if they're a werewolf. Well, having set those variables up, we're just going to look at each expression and work out what it evaluates to. Okay, so person 1 is a knight if and only if their statement is true, right? Person 1 is a knight, x1 is equal to 1, if and only if this condition here holds. Okay, so what does this condition say? Person 1 is a knight if and only if, or x1 is true, rather, if and only if the sum of the x's is less than or equal to 2. And we just dealt with this kind of condition. X1 is true if and only if the sum of these x's is less than or equal to 2. We just did this on a slide a moment ago, and you get this system here. So the x's have to sum to less than or equal to 2x1 plus 3 times 1 minus x1, and they have to sum to at least 3 times 1 minus x1. It falls just in line with those previous examples that we worked through. And I guess I won't bore you by looking at the two cases again. I hope you'll just trust me at this point. The second condition says person 2 is a knight if and only if person 3 is a knight, because person 2 said that 3 is a knight. So therefore, x2 has to be equal to x3. The werewolf must also be a knight based on the problem conditions. We have that xi is greater than or equal to yi, because the y's are the indicator variables for being a werewolf. And there's exactly one werewolf, so the sum of these y's has to equal 1. Now in this puzzle there was no objective function. We weren't trying to maximize the number of knights or anything like that. So we would just put a 0 in our objective function. And now I've just put out all those constraints I just listed here, and I can type this into CVX and solve it. And if I did, what I would find is that the first person is a knight and a werewolf, and the second and third people are knaves. So that's how you would solve that. And, you know, basically any sort of binary logic puzzle admits a solution of this kind, which makes integer programming extremely useful in terms of modeling and, you know, describing problems in a sort of codified way. The 8 queens puzzle is one that you might have seen before. The question asks you to find as many queens as you can. It has the number 8 in it, so it's going to turn out that the answer is 8, but we'll phrase this thing in terms of optimization. The 8 queens puzzle says you find a placement as many queens as you can on a chessboard where no 2 queens threaten each other. Now, if you haven't played chess before, I'll tell you that the queens in a chessboard can move any direction. They can move as many spaces as they would like vertically, or here, I won't do this one on the edge. That's not as general as I could be. I'll take this one here. This queen here can move as far as she likes to left or to the right, up or down, or diagonally. Okay, and you'll notice the way these queens are laid out. There's no queen in this board that is attacking any other queen if you just look at their spatial configuration. Okay, so we'll look at this in terms of maximizing. We'll say we pretend we didn't know the answer is 8, and we'll just say maximize and place as many queens as you can on the chessboard where none of them are attacking each other. And so how would you do this? Well, you'd have a variable, you'd have binary variables for each square on the board. It would be 0 or 1 to indicate if that square has a queen in it. Okay, and so I and j will go from 1 to 8 because you've got an 8 by 8 chessboard. And how would you do this? Well, you'd say each row can have at most 1 queen in it, right? You can't have 2 queens sharing a row because then they're attacking each other. So each row has at most 1 queen in it. So the sum of these x's, x11 through x18, is less than or equal to 1. x81 through x88 is less than or equal to 1. That just says the top row, the second from the top, third from the top, and so on and so forth down to the bottom has at most 1 queen in it. Also, each column, by the exact same reasoning, can have at most 1 queen in it as well. So you'd put in conditions like that too. And then also queens can move diagonally. And so, for example, you'd look at each one of the diagonals along that board there. You'd look at this one, and you'd look at this one, and so on and so forth. And you'd also look at these over here. You'd look at every diagonal on the board, and you'd have a condition for that too that says, you know, the sum of those entries has to be less than or equal to 1. So this is 3-1 plus 4-2 plus 5-3 is less than or equal to 1. So what is that? 3-1 and 4-2 and 5-3. Where would we see that one? 3-1 and 4-2 and 5-3 would be, let's see, 3 from the top, 3-1, and then 4-2. That would be saying that you can have at most 1 queen in this diagonal here. So that's the 8 queens puzzle. Minesweeper. This was actually a final exam problem a number of years ago, the first time I think I taught this course. Minesweeper maybe is not so popular anymore. It is a puzzle game that you play. It used to come with you know, Windows operating systems, and it was a way to teach you how to use the mouse. And it's a game that works like this. I give you a grid. Okay, you would be given a grid that looks like this thing on the left. And this grid has a number of hidden mines in it. Okay, and you would be told the number of mines at the start. And they're hidden. They're in these. They're not in the squares with the numbers. They're in these other empty squares, and some of them have mines in them. You don't know which one. The goal is to figure out where the mines are located. Now these numbers tell you for each square how many mines are adjacent to that square. Okay, so there's a 2 here, which says there are 2 mines adjacent to this square. And the adjacency can include diagonals as well. So by the fact that there's a 2 here, we know that there's a mine so if we look at these 3 squares here, we know that 2 of them contain mines. No more, no less. And the answer is written here at the right, that actually it's these 4 squares that have the mines in them. And you would be tasked with working that out logically. Okay, so that's what you're given. You're told this adjacency information, and you're told how many mines there are, and in this case here, there happen to be 4. So let's look at this from an optimization perspective, from an integer programming perspective. So what we'll do is we'll say, okay, xij is going to be a binary variable, again, 0 or 1, to indicate if a cell has a mine in it or not. And so anytime a number appears in a cell, now I'm going to use this example here at the top, which is a little bigger and a little more interesting. Anytime you have a number that appears in a cell, you know that that cell is empty. So here we'd know, for example, x11 is 0 because there's a 1 up there. x12 is 0 because there's a 2 up there, and so on and so forth, right? Any cell that has a number in it, we know that square does not have a mine in it. In fact, if you wanted, you could just not even have these variables, right? Depending on the flexibility of your modeling system, you could just not have them. I mean, I would look at this and say it's clearly a matrix, so why bother having a matrix with some entries missing in it? It's just as well to either have them or not. But if you have them, those variables have to be 0 if there's a number in that cell. Now, for every number that appears, we know that the sum of the neighbors of values has to be equal to the value in that square. And so, for example, you could look at this square here, and we'd say cell 3, 6 has a value of 2. So where is that? That's cell 3, and then so third row down, and then 1, 2, 3, 4, 5, 6. There's a 2 here, right? There's a 2 in here, and so what do we know? We know that all of these, if you sum up these squares next to you, and there are 6 of those, or 7 of those rather, we know that the sum of those has to be equal to 2. And so if you look at the coordinates of these squares, we know that x25 plus x26 plus x27 plus x35 plus x37 plus x45 plus x46 plus x47 has to be equal to 2, and so forth. We'll have 14 of these constraints because there are 14 numbers that appear up there. And finally, in this case, let's say there's 11 mines in total, and we could require a constraint on the total number of mines. That just says the sum of all these x's has to be equal to 11. So I can write those constraints in at any given instant in the board, and I can work out whatever information I can from it. It would be good, though, I haven't talked yet about what the objective function should be. Okay, when you play this game, you're clicking on squares one at a time. If you've played this game before, you'll know what I'm talking about. You're opening up, you're clicking on various squares and guessing that they're empty, and then if they're empty, you get more information, right? So as you play this game, you're clicking in various squares, and you're learning more information, which lets you click on more squares, and then hopefully, eventually, you figure out what the answer is. So we'd like to know, what is the best, quote-unquote, square that we should click on? Well, certain squares are probably guaranteed to be safe by the numbers that are configured, right? Probably there's some areas where you go, well, that square I know couldn't possibly have a mine in it because of certain conditions that are placed. Okay, some other squares maybe they definitely have a mine in them, and you don't want to click on that square. And then other squares might be ambiguous. You don't know. Okay, so how can we use optimization to figure out the optimal square to click on? One way to do it would be the following. Let's take every square and solve an integer program associated with that square. So let's ask this. Let's take square 6, 5, and we'll pick 2 different objective functions. So 6, 5, that's the 6th row down, and then 5 columns over, 1, 2, 3, 4, 5. That's this one over here. Okay. And let's think about this. Let's say, take all the constraints that I just said before, the ones that talk about, the sum of the mines has to be 11, and the, number of mines next to each number has to be whatever it is. Keep those constraints in there, right? We know those have to be satisfied. And let's put a maximize or a minimize as our objective function and see what that implies. Okay, let's say I said maximize x65, subject to all those constraints. Okay, I say maximize, it means make this as big as I can. Okay, what if I get a 1 there? Okay, what if I maximize x65 and I get a value of 1? Make this as big as you can, you get a value of 1. Then you're going to say, okay, well, that means it's possible that this square is unsafe, right? Because there exists a feasible solution where there's a value of 1 in that thing, in that square. So you'd say, okay, well, this might be unsafe. We know that much. But if I get a 0, if I say maximize this entry and I get a 0, then I'm very happy. It means I'm guaranteed to be safe in that square. Because when I'm adding an objective and I'm saying maximize the value, if that is equal to 0, that's telling me there's no possible way for there to be a 1 in that square. So if I say maximize the value and I get a 0, then I'm very happy and I know I can safely click on that square. If I do a minimize instead, if I say minimize the value of that square and I get a 0, then I know that, well, the square might be safe. It might be safe. If I do minimize and I get a 1, then it means that square definitely has a mine in it. Because when I try to make that entry as small as I can make it, I still get a 1. That means it's impossible for that square to be safe or to be free. Okay, so if maximize gives me a 1 and minimize gives me a 0, then I can't say anything. I say maybe, right? I say maybe it's safe, maybe it isn't. There's feasible solutions with both of them. And so what would you do if you're writing an AI to solve Minesweeper? You would just go through every single square and you would solve this maximize, minimize integer program for each of those. And then when they're both 1, it means you're definitely dangerous. If they're both 0, it means you're definitely safe. If the minimize is a 0, but the maximize is a 1, then maybe you don't know. You don't know if you're safe or not. And I've written the answers that you would get to this particular board configuration here on the right. So the greens have a letter Y. The green Ys mean yes, which means it's safe to play here. The red N's are a no, which means there's definitely a mine here. And then the brown M's stand for maybe, which means maybe it's safe, maybe it's not. So at this moment in time, you could click on every single one of these green squares and say, we're fine with that. And you could mark all of the red squares with a mine and say these are not safe. And then once you clicked on all those green squares, you'd gain more information and more numbers about what is close to what, which would enable you to solve the problem. So that's how you use integer programming to solve Minesweeper. A simpler problem, the world's simplest integer program maybe, is the knapsack problem, which is, you think of this as follows. You have a backpack or a knapsack that you're bringing on a trip, and it has a finite capacity. Okay, it can't carry everything. You have a bunch of things in front of you, and they have different values, and you're trying to get as many valuable things as you can into your knapsack without going over the capacity constraint that you have. So the way you'd represent that is you'd say C1 through Cn is the value of each of these n items. So you have a maximize objective, and then x1 through xn is a 0, 1 variable indicating whether you use that item or not. So you'd want to maximize C1, x1 sum through Cn, xn. That's the total value that you get from bringing all these things. And your constraint says that if the A1 through AN, if that's the weight of the object or how much space it takes up, then A1, x1 through AN, xn is less than or equal to B, where B is the capacity of this knapsack. So you're trying to maximize the overall value of the stuff that's in your knapsack, but you can't go over this weight requirement or volume requirement that bounds how much stuff you can have. Shortest path example, you have a network with distances defined on it. Okay, here's a network like that. And in this case here, we'll try and find the shortest path that goes from node 1 over here to node 6 over there. You'd like to find the shortest path that accomplishes this. And so how would you do this? Well, the natural thing is you'd say we'll have a binary variable for every edge that you would use. And actually what you end up doing is it looks just like that maximum flow problem that we looked at in one of the very first lectures. We'd let xij be a variable that indicates whether you use that link in the network as part of this shortest path. And what does the formulation say? Well, the value of this path, or the cost of it, is just the sum of the variables times the cost of that edge. So I'm adding up every edge here in my network, and I've got like a 9 here with x23. And where does that 9 come from? It comes from the fact that I've marked here that to get from node 2 to node 3, there is a value of 9. Okay, so this objective function here measures the total cost of all of the edges that I am using. And then what has to be true? So I have to leave from node 1, which means that you take all those edges that are leaving node 1, that's 1, 2, 1, 3, and 1, 5, that has to sum to be equal to 1 because you have to be leaving from node 1. So one of those has to be used. You also have to be entering node 6, and so therefore 3, 6 to 4, 6 to 5, 6 has to be equal to 1 as well. Now for every other node, what has to be true? You have to make a path, which means that anytime you enter a node, like say I enter node 5, you have to leave that node. All right, and so what does that mean? It means you go through every node, as I've done down here, here, and here, and here. And I've said for every node, you look at the edges that are entering you. So this is node 2. And you look at the edges entering you, which is 1 and 2 and 6, 2. So let's go to node 2 and verify that. Clean off some of the space here. Okay, here at node 2, you've got 1, 2 that's entering you and 6, 2 that is entering you. And then what is leaving node 2? 2, 3, and 2, 4 is leaving node 2. So let's look over here and we can see, yeah, over here leaving node 2, you've got 2, 3, and 2, 4. So if you're using anything entering node 2, you have to use something that is leaving node 2. Ditto for node 3 and leaving node 3, and ditto for 4 and entering node 4, leaving node 4, and then also for x5. Okay, so that's the shortest path formulation. That's how you, have to impose that you have a path. Facility location. Facility location is a generalization of this transportation problem, the problem where you had the warehouses and stores, but you have additional attributes that are complicating things. So number 1, the total supply is greater than the total demand. Okay, and maybe it's infinite. Maybe you actually have an infinite supply available. Okay, so you have more supply than you need. And also each supply node now has a cost that I have to pay if I use that node. Okay, so some of these supply nodes, I used to call them warehouses. Now we're calling them facilities. Every node on the left has a cost that's attached to it, and you have to pay that cost if you use that node. And so the goal is to minimize the sum of these transportation costs from moving things from left to right, just as you saw in the transportation example, together with the fixed cost of actually using these nodes on the left. Fixed costs are binary because you just pay a fee or you don't if you use the node or not, whereas the transportation costs are continuous, and so we'd say this is a mixed integer linear program. Okay, and if you look carefully here at the diagram, I'll talk about what's going on. I've zoomed in a little bit so you can see some of the numbers here. You look here at the left, I've got a lot of numbers. So I've got the amount of supply that each of these warehouses has at the left. I've got 6, 4, 4, and 3, so add that all up. That's 17 units of supply in total. And in demand, I have 1 plus 4, that's 5, 6, 7, 8, 11. So 11 units of demand versus whatever the number was I said, 17 units of supply. Okay, so more supply than demand, as we said. I've got all these numbers here that indicate the transportation cost. So if I've got a number 8 here, for example, that's because it cost me $8 or whatever the cost units are for every unit that I send from this first warehouse over to this second store, like that. Okay, and now finally, within the warehouses themselves, in addition to the costs, as I've drawn here, the 6, the 4, 4, and the 3, the amount of supply that I had here, 6 units of supply, 4 units of supply, and so forth, I've got the costs too. So using this warehouse at all, if I'm using it even just for one single unit, I have to pay a fixed cost of 3. It's like a cost of building, or activating a site or something, right? It's the cost of making any use whatsoever of that factory. So those costs are 3 plus 2 for this one, 8 for this one, and 5 for this one over here. Okay, and the solution that I've sketched is here on the right. If you look at that, so the optimal solution says you should use the first and third and fourth sites. And what would the cost of that be? The cost for that would be 3 plus 8 plus 5. So 3 and 8 is 11, and 5 is 16. So 16 for that. And then here's your transportation plan too. You send 1 unit to this thing, and then 3 units down there, and 3 units here, and so on and so forth. Okay, so that's the solution. It's the transportation problem, but with this added layer that you're trying to decide which sites you should even be using at all, or which warehouses you should be using at all. The way this integer program works is you're now going to have 2 sets of variables. You're going to have xij, as we had in the transportation problem before, and we'll say those are actually going to be continuous variables because they model how much you're transporting from the left to the right, and we'll assume that that's allowed to be fractional because it always has been in our previous problems already. And now in addition, you have yi for each one of these sites on the left, and that's a binary variable. It indicates 0 or 1 whether you decide to use that warehouse or not. You decide to use that node on the left. So what does our objective function look like? Well, you have those transportation costs that you had before, just the sum of the overall cost of transportation, as in the transportation problem. And then in addition, you have these extra 4 terms. These are the cost of using each of those 4 facilities, right? We said it's 3, 2, 8, 5, and that comes from the previous fixed cost of 3, 2, 8, and 5, like that. So that's how our objective function changes. We have this extra expression there. And then you have the same kind of the transportation conditions that you had, or meeting the demand rather, which is, the first demand node has to get 1 unit of supply from these warehouses. So x11 plus x21 plus 31 plus 41 is equal to 1. And then the second store, we're calling them, has 4 units of demand that it requires. And so the sum of the stuff coming into that second store, or whatever you want to call it, has to sum to 4. So those all go just fine. And then what's the last thing we need? What changes the problem? What changes the problem is that if I'm not using a facility, or if I'm not building the facility and am therefore not paying for it, then I'm not allowed to ship anything from it. And so how would you write that? So what I would do here is, let's look at this constraint here. That says 1, 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, 5 plus 1, 6. That's all the stuff that is leaving the first facility, right? It's going to these 6 customers. That's all the stuff that's leaving the first facility. And I said that's less than or equal to 6 times y1. All right, what is going on here? Well, number one, if y1 is equal to 0, then it means I'm not building anything at that site. It means I'm not using that site, right? If y1 is 0, then I'm not paying for using that site there. That means, so in the previous example there, y2 would have been equal to 0 if I can pull that back up. See, in the first example that I had, or the previous example, you weren't actually using that second site. So y2 would have been equal to 0. Okay, so on the one hand, if y1 were equal to 0, it means you can't send anything because you're not using that place. However, if y1 is equal to 1, then this says that the sum of all that stuff leaving the first site has to be less than or equal to 6. And where does the number 6 come from? 6 comes from the fact that, let's erase this here, 6 was the number of units of supply that that first warehouse had. Okay, 6 units of supply, like that. So because you have 6 units of supply, therefore the sum can't exceed that. As I said before, sometimes you have an uncapacitated problem where you assume that each of these facilities has, can provide an infinite amount of supply to all of the customers. And if that were the case, that 6 would just be replaced with some, ludicrously high number, right? Maybe it's the total amount of demand across the entire network or something like that, which you're never going to exceed. And so that's facility location. That's how you would solve this problem. One last sort of aside comment is that there is a graphical method for solving integer programs in 2 dimensions. So for integer programs with only 2 variables, not much changes about that graphical method, and here's how I would describe that. If I give you an integer program with 2 variables, and I say solve this problem using the graphical method, here's how you can do this. Number 1, forget about the integer constraint. Just draw the feasible region like I've done here for the linear program. Okay, don't do anything unusual about that, just draw it. Okay, and then step 2 is you look at the integer points that are contained inside that feasible region. Okay, that's these that I've drawn in here, and which I'm indicating with my pen. All right, and then what you do is take an imaginary rubber band and wrap it around these integer points. Okay, which gives you this thing. I don't know what this toy is called, but in kindergartens and in elementary schools, kids often have it sort of a wooden board with nails poked in it, and you wrap rubber bands around them to make shapes and things like that. I don't own one, but maybe you've seen one of these. And now what have I accomplished by doing this? Okay, let's look at this dark shaded region in here. This is called the integer hull of these points, and let's look at this very carefully, and I'm going to trace it. What is interesting about this dark shaded region, which I obtained again by taking the linear programming relaxation. I took the linear programming version of my problem, and then I highlighted the integer points inside that set, and then I wrapped this imaginary rubber band around those points. What's interesting about it is that all of its corners, sort of by construction, have to be integers. Right? Because I'm just taking a rubber band and I'm wrapping it around these imaginary pegs. So you couldn't have any corners that are not an integer. And therefore, then what can I do? I can just solve my graphical method linear programming problem on this dark shaded region here. And then whatever corner I land on is guaranteed to be an integer anyway. So having done that, therefore, I've just done a pretty minor extension or a minor variation on the graphical method to come up with a means of solving that.